Right. Okay, so let's start by remembering where we were at the end of the last lecture. So we had decided on the basis of a somewhat crude estimate that when you have some region, then the entanglement entropy, let's say in the ground state or some reasonable excited state, has a leading term which is proportional to the area of the boundary of the region. So this is what we call the entangling surface. In units of the cutoff. So this is what's called an area law divergence. And subleading things which are also proportional to the area, but have other dimensionful quantities, for example, the correlation length, if we're in a massive theory. And we finally expect there to be terms which actually are independent of the cutoff. And there can also be terms like, in certain dimensions, it turns out that when D is odd, you also get terms that have logs. For example, something that looks like this, times log epsilon over xc. Turns out that terms like this only appear in odd dimensions. All of this is the stuff that's proportional to the area, but there's also, of course, terms that depend on the shape. Okay. And the name of the game here is to forget about this stuff that depends on the cutoff, because that's all kind of dirty regulator-dependent stuff that doesn't actually capture properties of the continuum field theory that we're trying to model here. And the leading, if you have a term like this, then its coefficient, or if you don't, then the coefficient of this one is cutoff independent, sometimes called universal, although I dislike this term because it's overused. It means a lot of different things depending on the context. But what I really mean by this is that it is a property of the continuum field theory. And what we want to do, and within here, there are similar terms. And the name of the game is to extract that good stuff from the noise. So in other words, some kind of subtraction or renormalization. There are various kinds of subtractions you can do. You can, for example, take derivatives with respect to the size of A, or you can look at some quantity where it's explicitly subtracted, because it turns out that all divergences, all divergent parts of the entanglement entropy are local on the entangling surface. And therefore, any quantity like the mutual information, as long as you're doing a subtraction that again is local, you will cancel all of the divergent quantities. And you're left with stuff that again characterizes the field theory. This is assuming that A and B don't share a common boundary. It fails if you talk about something like this, because then you have a persistent divergence along their shared boundary. So this is the sort of thing we'll be doing. Another thing I want to say, well, any questions about this? I mean, this statement, I haven't proven to you that all divergent parts of the entanglement entropy are local on the entangling surface. That doesn't mean that they are only from this term. They might be shape dependent. There are divergent pieces which depend, for example, on the integrated curvature of the entangling surface, but they're still local, meaning they're integrated local quantities, okay? And hopefully this is sort of a reasonable statement in that, you know, everything that's divergent by definition is reflecting, you know, microscopic physics on the scale epsilon, and so you expect its contribution to the entanglement entropy not to know any global information about the shape or the size of A, but simply to be an integral of some local quantities. Another thing I want to point out, so far this was sort of assuming that the full system is in a pure state, but you can also talk about this entropy, let's say when the full system is in a thermal state. So put the field theory at finite temperature, and then there's another piece which is actually, everything so far has been proportional to the area or a lower power of the size. So in other words, if this thing is characterized by some length L, then everything on the board is L to the d minus 1 or lower powers of L, okay? But as soon as I'm at finite temperature, then I'll have an entropy density, so L to the d, a volume law term, not divergent, so no epsilons in it, assuming my temperature is well below the cutoff, so I have some finite temperature, then I will get a contribution which is a volume law and which doesn't reflect entanglement per se. This is the extensive entropy density. This will be the leading term at large L. And then, of course, there may be other terms which are more interesting. I mean, in some sense, this is not a very interesting term, but it is there. It doesn't tell you anything about entanglement, it's just the thermal entropy density. But then there may be other terms which are maybe more interesting, which depend on the shape of A in some non-trivial way, also at finite temperature. Okay? So there's all kinds of things you can study. You can calculate, write tons and tons of papers with all kinds of calculations of these things, to the extent that you can calculate these things. Which brings me to my next point, which is an example where we're actually going to do the calculation in full detail. And it's kind of the simplest possible case. But actually, before doing that, I remembered I wanted to just give a quick overview of after doing my review of the lecture, of what I'm going to try to accomplish today, give you a picture. So I'm going to do this example, which is a spin system, which has a nice continuum field theory limit, and we're going to calculate the entanglement entropy. And we're going to see how you extract universal parts, regular independent parts, from the entanglement entropy. And then I'm going to switch gears and just say, okay, we're now talking directly about quantum field theories. And I'm going to forget about regulators, and I'm going to forget about spin systems. And from then on, I'll be talking about relativistic quantum field theories. And we're going to try to understand the structure of the entanglement entropy in relativistic quantum field theories. And in order to make more progress, then we're going to specialize more. And in particular, we're going to talk about one-dimensional conformal field theories. By reducing the dimensionality and increasing the amount of symmetry, we're going to be able to make more progress and be more explicit. And I'll talk a little bit about two-dimensional conformal field theories, which are also rather well understood, and try to illustrate some of the power, some of the dividends you get from thinking about the entanglement entropy. So in other words, some of the new things about quantum field theories that have been learned from studying entanglement entropies. Maybe I'll cover, half of 1% of what you can do with entanglement entropies in field theories, but just to give you a flavor of it, okay? Okay, I may have had some numbering system for my sections. I think this may have been A, the spin systems. Anybody who's taking notes, you can recalibrate at some point. But let's pretend like it was like this. Okay. The explicit example I want to do is called the Taric code. And it's a two-dimensional spin system on a lattice. We have some infinite lattice, square lattice. And the spins live on the links, not on the sites. So we have a spin and a half on each link. And it's basically, if you're interested in entanglement entropies, it's kind of as simple as possible, but no simpler. And here's our Hamiltonian. So we have some overall energy. And then it's going to be a sum of terms. And let me just write down, and then I'll explain what these mean. So V is a vertex. Where four links meet, and P is a plaquette, which also includes four links in a little square. And remember, on each link we have a spin and a half, so we have Pauli operators, and HV for a vertex is simply the product of all of the sigma z's. So sigma z1, sigma z2, sigma z3, sigma z4. And the plaquette operator is a product, there's no product here, sorry. Is a product of all of the sigma x's, sigma x1, sigma x2, sigma x3, sigma x4, going around. Okay? And the Hamiltonian is basically minus the sum of all of the vertex operators plus all of the plaquette operators. And it's very important to note that all of these terms commute with each other. That's pretty easy to see. I'm not going to work it out. But so, of course, there are, so if you have something like this, there's a vertex operator here and a plaquette operator here, and it's easy to see that they commute with each other. Similarly, the vertex operators all commute with each other because they just involve sigma z's, and the plaquette operators all commute with each other because they involve just sigma x's. So, so aren't we lucky? All the terms in H commute with each other, which means that the ground state. Which means that the ground, or all of the energy eigenstates, are states that are eigenstates also of each term separately in the Hamiltonian. And in particular, the ground state is the one where all of these have their maximum value, and their maximum value is 1. So HV, for example, for a given vertex, has eigenvalues plus or minus 1. HP also has eigenvalues plus or minus 1. So the ground state is just a state, assuming there is one, in which HV, all the HVs have eigenvalue plus 1, and all the HPs have eigenvalues plus 1. Okay? Simple enough. Okay, let's see if we can find such a state. Yes?
Maybe it makes sense. Why does the plaquette operator commute with the vertex operator?
Because they meet on 2 links, and so 2 of these guys are going to anti-commute with each other. And when you have 2 minus signs, you get a plus sign. Are we good? Okay. Let's first solve this constraint, and then we'll solve this constraint. So this means if I color spin up white and spin down orange, then we have various possible configurations. It means that you have an even number of spin-ups. Okay, so it can look like this. It can look like this, like this, etc. Okay, or like this. Okay, as long as you have an even number of spin-ups. Okay? And that happens at every vertex, which means that the number of, if you think of this as like a flux, the flux is conserved, or is conserved mod 2, because we can only keep track of 1 unit of flux on each link. Flux is conserved mod 2 at each vertex. Okay? So we basically have a very simple version of a Gauss law going on here. Okay? And so an allowed configuration has some set of flux lines going around that they can cross each other. And in fact, they're not even sort of distinguished so much. I can have something that goes like this, and anything I want, as long as at each vertex the number of flux lines is conserved. Okay? So a configuration where, so satisfying this Gauss law, is called a string net. Fancy term. Well, I'm calling it a unit of flux if it's spin up on a link. And if it's spin down, I'm calling it not a unit of flux. Okay? And now it's time to impose, so anything that obeys the Gauss law obeys this constraint, and now we want to impose this one. And what does the plaquette operator do to a string net? Well, it flips all four flux units around this plaquette. So it turns something, so if you have something that's going along like this, for example, it'll delete these fluxes and move it over here. So it takes a string net and gives you a different string net. If you had nothing, it would create a little loop of flux. So it just moves the string net around to give you a different string net with coefficient 1. So I think it's pretty clear, I'm not going to try to argue this rigorously, that this constraint basically means you better have a linear superposition of all string net configurations with equal weight. Okay? And with no phases. That's our ground state. Okay? Now, this, yeah, because I can always create little loops and move them around and everything. So, and you always, by applying one of these operators, you always change the state. So in the basis that we're working in, so any string net will be changed. No string net is left invariant by any of these operators. Okay, so it always takes you from one string net to another. And so, yeah, so I think it seems reasonable that you end up with just, there aren't different sectors or anything like that that don't get mapped to each other, as long as we're in infinite space. Now here I might mention why it's called the Toric code. It's called the Toric code because it gets more interesting if you put this on a torus, because then you do have a conservation law, which is the flux around the cycles of the torus is not changed by acting with this, and you get a degenerate ground state. In fact, you get a fourfold degenerate ground state because the conserved quantities are the total flux around each cycle, which can be 0 or 1. And so you get fourfold degenerate ground state. And it turns out that if you're working in, if you put this thing on genus G, on a genus G surface, you get a 2G degenerate ground state. Okay? So that explains toric. This ground state, well, the one we're working with is unique, but this statement would be true even if we were on a torus or something, is gapped. So it's pretty clear that the first excited state, let's say, is achieved by breaking one of these rules, which means that, and it'll have, you know, energy plus 1 in units of h naught. And so there you'll have a string which kind of ends somewhere at some point, okay? Or if you violate this rule, then you're basically saying that you're forcing the flux around some given plaquette to be 0 or 1. So you're not allowing that particular flux to fluctuate. And so essentially the excited states are given by inserting defects at particular points. okay? And it turns out that, so this is a gapped ground state. And the excitations are defects, which turn out to have anyonic statistics. So there's a whole interesting story there, which I'm not going to talk about. And what does this thing look like at long distances? Well, it's a gapped ground state. So at long distances, it looks pretty boring. Okay, there are no low energy fluctuations. Okay, so there are no massless fields. Okay, with no massless fields. And furthermore, because everything is fluctuating so much, there are no long-distance correlations. So there are no non-trivial correlation functions. So you might think that this is the world's most boring field theory, that it has no content whatsoever. But you already know that that's not true because I told you that if you put this thing on a torus, you have degenerate ground states. So, and that torus could be very large, okay? So this theory actually has what's called topological order. And it's what's called a topological quantum field theory. And it's called the code because essentially you can use this whole setup as a quantum error correcting code where you use the excited states to store information, and the idea is that noise, as long as it's localized and is kind of low energy, doesn't change which state you're in. So for example, so there's a few things you can do with it, which I don't want to go into in any detail, but for example, if you put it on a torus, then you can store information in which of these degenerate ground states you're in, and then localized perturbations of the system won't change that, okay? Or you can use the anyons to store information. Okay, but our interest here is not in using it as a quantum error correcting code, but in calculating the entanglement entropy. So let's cut this thing up. And in some way, oops, I did that very poorly. I wasn't paying attention. When we cut it up, sorry, I was cutting it up the way I was cutting up my earlier thing, but what I should have done, I really messed up my drawing here. What I should have done is made the entangling surface go through the vertices because it is the links where the spins are. Okay, so that's my entangling surface. And at each vertex, we know that the flux is conserved again, which means that from the point of view of the inside, the total flux coming in is determined by the state of the outside. So we want to know to what extent the inside and the outside are entangled with each other, and they're entangled via this Gauss law constraint. Okay? So once you trace out the outside, you have some quantum state on the inside, which is going to be a mixed state because two pure states of the inside that have a different flux numbers, let's say at this vertex, are essentially decohered with each other. Okay? So essentially if we diagonalize the mixed state we get, the reduced density matrix, those eigenstates are going to be characterized by the flux through each vertex. Okay? So that means that the number of them, the log of the number of them, is the entanglement entropy. So at each vertex, we can have either flux 0 or flux 1, because all the fluxes are mod 2. Okay? Either one is possible. I think it's pretty clear that they have equal weight. Everything in here has equal weight. Okay. And so that means that the entropy is log 2 times the number of vertices in the entangling surface. And this is our area law divergence term, as promised. Except I've forgotten one thing, which is that there's a constraint on the fluxes. And in particular, if A is connected, the total flux through dA has to be 0, mod 2. So there's actually a missing degree of freedom in describing the state of A, the reduced density matrix of A. So there's one fewer degree of freedom than you would naively have thought due to flux conservation. And that's a global constraint. So this is incorrect. The actual number is this minus 1. And this second term is very interesting because it's independent of the cutoff. Okay? And if I have one connected component, but imagine that A, let's say, has two connected components, then I have a separate flux conservation law. The total flux going through dA, going through each component of dA, is 0. So I actually have minus n, where n is the number of components of A. Okay? And in fact, in general, so this we can write like this. So this is sigma over epsilon minus n log 2. This is the interesting part. And in fact, for a general massive theory in 2 dimensions, the entanglement entropy looks like this, where gamma is called the entanglement entropy, assuming this is for dA smooth and large compared to the correlation length. So basically, I'm dropping all of this stuff. So we're really taking a very large region, which is not only large compared to the lattice spacing, but large compared to the correlation length. Okay? And then all you're left with, besides the area law term, is some finite term, which is proportional to the number of components. And this gamma here characterizes the theory, and it's called the topological entanglement entropy. And you could ask the question, so at very long distances, any massive theory has no non-trivial correlation functions left, so it's described by a topological field theory, which may be trivial. Okay, so the gamma may be 0, but in a case like this, it's not. So it characterizes whatever your topological quantum field theory you have in the infrared is. And in fact, in a very precise way, there's a formula that you can derive relating gamma to the anyon spectrum. So when you have a topological field theory, it's kind of characterized by the spectrum of anyons it has, in other words, defects, and you can write a formula relating gamma to that. So this is the kind of data you want to have for your system. And you could ask the question, well, this is great, but how the hell am I ever going to know what this is? Isn't it swamped by this divergent piece? Like if I'm calculating on a computer my S of A, how am I going to extract this? So there's a couple ways to do it. You can you can take derivatives with respect to the size of A. So you can compute, you can take A to be a circle of radius r, and then you compute r ds of A dr minus S of A. And this will tell you gamma. That cancels out this term. Or you can do something fancier where you look at this kind of configuration. And then you compute this particular combination. And this particular combination is sometimes called the tripartite information. And you can work out that these differences, what they do is they subtract out the area term on every single edge. So the area term on every edge appears twice, once with the plus sign and once with the minus sign in this combination. Now these are not smooth. So this formula actually doesn't apply here, and there are extra divergences at the corners, but you can show those also cancel. I don't want to go into that. So this, okay, and this work is Kitaev and Preskill and Levin-Wen. This was one of the first cases where people realized that this entanglement entropy is really useful because it's a very difficult problem given some spin system to know whether at long distances it has topological order. Even if let's say you can simulate it on a computer, because there are no correlation functions to compute, okay? This is actually a very efficient way to do it. You compute your entanglement entropies, and then you do one of these things, and you learn what gamma is. And if gamma is non-zero, then your system has topological order. Assuming that it's not critical. Hopefully you can tell whether your system is critical or not. Okay, that's the Taric code. Any questions? Yeah.
Somehow the entire picture hinges on the fact that you are considering a massive
So I'm gonna.
kind of richer story.
It's not actually that much richer, but I'll talk about that. Yeah. This one? Well, I didn't go through the algebra, but you know, heuristically, the entanglement occurs when there's some correlation in this state between the inside and the outside. The only correlations in this state occur because of the Gauss law constraint at the vertices that lie on the entangling surface. Every time you have a vertex that lies on the entangling surface, you have a correlation between the inside and the outside within this state. So if you believe that, then the entanglement entropy is given by the number of vertices. That was if the vertices are independent. They're almost independent, but not quite. So that's my words derivation of this formula.
So in this case, sigma over 2 is
In this case, gamma is log 2. What do you...
sorry.
Sigma is O. Well, sigma is the area, I mean, I'm sort of using, I mean, yeah. You know, it's this term, log 2 times the number of vertices in dA is kind of what I mean, yeah, by the area of dA in units of the lattice spacing. You know, the only degrees of freedom that this theory has at low energies is the total flux, you know, sort of global flux quantities. That's why if you put it on a torus, it's just the total flux around each cycle, okay? And so this flux conservation is this global constraint which knows about the whole entangling region at once, entangling surface at once. If we had local degrees of freedom, you know, local excitations, we would get other contributions, okay? But notice that this is a negative contribution, okay? There's less entanglement than you would naively have thought because of the topological order.
N here is 1, then, right?
In this picture, it's 1.
Okay.
Yeah. And you see from this, by the way, that the mutual information, this implies that the mutual information for disconnected regions, for separated regions, is 0. Which means that there's no correlations, which explains why all your correlation functions vanished. So if this is 0, then the reduced density matrix is a tensor product, and the correlation function between anything, any operator in here and any operator in here has to be 0, which it is. What? Right, so this is where this comes in. So I've assumed that everything is large compared to the correlation length. Yeah. Okay. I'm done with spin systems, and I want to move on to relativistic quantum field theories. And here, it gets harder to make explicit statements. So I'm just going to make life as simple as possible for myself by considering the simplest possible question, which is what is the entanglement entropy in Minkowski space in the ground state of half the space. Okay? So this goes the name Rindler space. Well, I'll define what Rindler space is in a second. I'm just going to assume we have a relativistic QFT in Minkowski space in the ground state. And I'm going to take A to be the half space where my x1 coordinate, so x1 is in this direction, is positive. So this is my A, and this is my A bar. Before we try to compute the entropy of this, I want to explain the term Rindler space. So if you had rho sub A, so of course by definition, rho sub A, you get the expectation value of for any operator in this half space, and it doesn't have to be local, it could be some product of local operators or anything you want, but not just there, because if I have some, so far this picture is all at t equals 0. So let me actually, since we're doing relativity, let me introduce time into the picture. And I have some other dimensions going transverse to the board, which I'm not going to attempt to draw. And my A is living at t equals 0. So this is A. And if I have some operator which, using the field equations, I can map back to an operator that lives in A, then I can compute this using rho sub A. Now, the field equations always move operators around within the light cone. So, in fact, I can compute this for any operators living inside the causal domain of A. Which is this wedge. So once I know rho sub A, I know everything that any observer could observe who lives inside this causal domain. And this causal domain is called Rindler space. Now, if you are an observer who is confined to Rindler space, what you have to do to stay inside Rindler space is you always have to keep accelerating. If you follow any time like geodesic will leave Rindler space eventually. So the observers who live in Rindler space are in a funny position. They're always accelerating their whole lives. And as far as they are concerned, there is a horizon. There is some part of the space they cannot observe. So for them, this is a future horizon, this is a past horizon. It's like they live outside of a black hole, or it's like for us in our universe, we have a cosmological horizon which surrounds us, okay, past which we can't see. So observers in Rindler space have a horizon, and because there's part of the space they can't see, they live in a mixed state, okay? one observes a mixed state, namely rho sub A. Now, what can we say about rho sub A? So here we're going to use some quantum field theory tricks. Specifically, we're going to go to a Euclidean path integral description. Oh, yeah. And we're going to try to be explicit about what this rho sub A is. Now remember, that by definition, this is the trace over A bar of this. So first we need a description of the ground state. And there is, thankfully, a description of the ground state using the Euclidean path integral. So now I switch to Euclidean space, and I have some Euclidean time tau, this direction. And here's my x1. Yeah, this is my x1 direction. And then again, I have other spatial directions. And I want a description of, some description of this ground state. And it turns out the ground state can be described as follows. So essentially what I want is a wave functional. So the wave functional is the ground state in the basis where my fields take definite values at some given time. So let me call that phi naught of x at t equals 0. So this is my wave functional, my ground state wave functional. And just like in quantum mechanics, you can get the ground state by evolving in Euclidean time for an infinite amount of time using your Euclidean Hamiltonian, because then the Euclidean time evolution operator, instead of being unitary, it's like e to the minus beta h. And so it projects out everything but the ground state. Okay, everything but the ground state gets exponentially suppressed if you start from any given state. Okay, so we're going to evolve for an infinite amount of Euclidean time up to t equals 0 or tau equals 0. Okay? So that's my picture, and what I mean by this is the following. Path integral over my fields. E to the minus Euclidean action with the boundary condition that phi at x naught equals 0 equals phi naught of x. Let me adjust my notation slightly to be consistent. A little simpler. Okay. So I have a boundary condition where for any phi naught, my field takes some definite value. It's like a position eigenstate, but a field eigenstate on this tau equals 0 or x naught equals 0 boundary. And then I do the path integral everywhere down here for x naught negative, let's say. And whatever I get, whatever amplitude I get, is the wave functional up to there's some normalization factor. I'll explain why I'm putting square root there in a second. Okay, so I have a way of computing my ground state wave functional, at least formally. Now, that's the ket. The bra is given by flipping my Euclidean time. So this thing, so this rho, so given some phi naught rho phi naught prime, which is phi naught 0, 0, phi naught prime, Well, this is just, of course, just the product of two things. This, again, is tau, which is x naught. And here I put, just like before, here I put the boundary condition phi equals phi naught. Here I put the boundary condition phi equals phi naught prime. And I just get the product of these two things. Okay, times 1 over z. Now, the interesting thing is what we're going to do now is we're going to trace over a bar, which means we're going to integrate, we're going to set phi equal to, we're going to set phi naught equal to phi naught prime and integrate over them. So when I set them equal on a bar, that means that these are not independent anymore. Up to here, they have to equal each other. So the field here has to equal the field here, and then I integrate over all possible values. Well, that's the same. I can draw that. We'll get a nice picture. We still let on A phi naught be different from phi naught prime. So I'll write this phi naught A, rho A, phi naught prime A. Well, yeah. And what is that? Again, set the field here equal to the field here and integrate over all possible fields. But on A, let them be independent. Remember, this is an operator. This is an operator only on A. And do your path integral everywhere else. And here you have phi naught A prime, phi naught A. And what is this? Well, this is an operator that takes a state on here and maps it to a state on here. How does it map it? It maps it by doing a Euclidean time evolution, but not in the Euclidean time direction, which is like this, but around the circle. So it's a Euclidean time evolution through a time 2 pi with respect to a rotation in Euclidean time. Okay? So you have an operator which rotates you in Euclidean time, and this rho sub A is 1 over z times e to the minus 2 pi r, where this is the generator of Euclidean rotations. But what is the generator of Euclidean rotations? Well, once you flip back to a Minkowskian point of view, if you think about it, it's a boost. So this operator, I'm not going to try to prove this, but this operator is also the same as the generator of boosts in Minkowski space. And the generator of boosts is basically an integral of the stress tensor, because the stress tensor is responsible for all of your kind of translations and all your space-time movements, basically, including boosts and rotations and translations and so on. Okay, so there's a formula for R, which is that it's the integral dx, d minus 1x, and then integral from 0 to infinity dx1 t00 times x1. So T00 at a given point tells you the response to a translation, and here the translation is proportional to x1, right? I mean, if in a rotation picture, the amount for a given angle by which you move, let's say you move an infinitesimal angle epsilon, the amount by which you move is epsilon times x1, and so you get T00 times x1, and that's also true for a boost. Now, when you look at this should look somewhat familiar. This is not just some random state. This has the same form as a Gibbs state. So that means that this state, so rho sub A, is a thermal state at a temperature 1 over 2 pi with respect to the Hamiltonian R. So that means that the observer who's stuck in Rindler space, let's consider, for example, an observer at a given position so let's say an observer who stays at a given proper distance from the origin. This is her world line. So this is x1 squared minus x naught squared equals, let's say, L squared. That observer is living in a thermal bath. At what temperature? Well, the temperature formally is 1 over 2 pi, but the local temperature is 1 over 2 pi L, because at t equals 0, x1 is L, and basically, locally, the observer feels like, well, at that point, the generator here is T00 times L. T00 is simply the local energy density operator, okay? So the observer let me avoid writing the word feels in a physics lecture, at least writing it on the board. The observer is effectively, let me write this. At a local temperature, sorry, in a thermal bath at a local temperature 1 over 2 pi L. This is called the Unruh effect. And you can actually show that if you put a particle detector in Minkowski space on an accelerating trajectory, the particle detector will detect a thermal spectrum of particles at that temperature due to the acceleration, okay? Okay, this equation here is due to these folks. So Unruh was in the early 70s. Didn't I write this down somewhere? And then these guys. So in particular, the fields near the horizon over here are very hot. okay? So the observer, if the observer is near the horizon, then she feels very high temperature, okay? Now, what we haven't done, of course, is computed the entropy. We have a formula for the state, and in principle, one can then compute entropy from this state by doing rho log rho. Of course, doing that in practice for a real field theory is very hard, but let's just get it. I mean, it can be done in simple cases, I want to just get an estimate of the entropy. This is going to be a somewhat crude estimate, but it's based on the fact that the fields, the closer you get to the horizon, the hotter the fields are. And what I'm going to assume, which is not really true, but I'm going to assume that the entropy is just an integrated local entropy density, where the entropy density is determined by the local temperature. That's my first approximation. My second approximation is going to be that that entropy density has a very simple form. But it is true that the order from this point of view is that the fields, the closer you get to the horizon, the hotter they are. The reason they're hot is because they're entangled with a bar. Okay, so you have these modes which are being cut in half and lead to entanglement, and so they're in a mixed state. And this mixed state happens to be very simple. Okay? So the local, so let's say we have a field with mass m, then very roughly speaking, the entropy density if the temperature is above the mass, is sufficiently high above the mass, then by dimensional analysis, it's T to the D, because it has to be a quantity which, when you integrate over D spatial dimensions, is dimensionless. And if T is sufficiently larger than M, then it doesn't depend on M, so it has to be T to the D times some coefficient. And if T is less than M, then you can't excite the particles. Okay, this is an incredibly crude estimate of the entropy density, and I'm going to continue to be very crude and just integrate this with respect to space. Okay? So this is just to get a feeling for what you have. So integral dd minus 1x, integral dx1, s of t. This guy gives you sigma, our old friend, which is the volume of the entangling surface. So this in this direction. Okay, so we cut it off somehow. I mean, it's infinite in Minkowski space, but cut it off. You get some area. And then you get an integral. But now you see, so a priori what I want to integrate is x1 dx1, x1 to the d, because my temperature as a function of x1 is 1 over 2 pi x1, and I'm dropping the 2 pi's. And I think I might have messed something up here. Oh, minus d. Okay, again, the smaller x1 is, the hotter it is. And you integrate only up to 1 over m by this rule. Okay, so once you're out past 1 over m, the fields are too cold to be excited. You have a mass gap. They're too cold to be excited out here, so you only integrate in here. But you've got a problem because in here you get a divergence. So we better cut this off over here. So we integrate only down to some cutoff epsilon. There's our regulator again. And when you do the integral, you get sigma times 1 over epsilon to the d minus 1 minus m to the d minus 1, which actually is the same estimate we got before from our spin system. Yeah?
Why should the entropy go like
Well, I mean, this is totally fake. This is really, but at very large, when the temperature is sufficiently larger than the mass, then it's like the mass is 0. And the only dimensionful thing is the temperature. Yeah. So we recover from this Rindler point of view what we had before from the spin point of view, which is nice. Okay? It's just a different point of view on the same thing. And of course, it has the same, you know, there's all the other terms in between these two and stuff, you know, and then, you know, and of course, there's no shape dependence because by definition, we've started from just a half space. So you wouldn't see whatever shape dependent terms there might be from this calculation. Okay? And that is Rindler space. And it's very rare. This, you know, you might not know how impressed to be with this formula, but it's very rare, and it's only because we have such a simple setup here that our reduced density matrix has a Gibbs form where the Hamiltonian is an integral of a local operator. There's usually no such, the rho sub A, there's no reason for it to have such a form normally. Any questions before I get more specialized? So to make progress, I'm going to, like I said, get more specialized, and I'm going to reduce the dimension to d equals 1, and I'm going to give myself conformal symmetry. Now actually here, if you look at this, this wasn't quite right in d equals 1, because actually you get a log. So this thing actually is saying, there's no sigma because there's no other x's. But this says that S of A should be log m over epsilon, which goes to infinity as we take m to 0, as we take the massless limit. And so we have an IR divergence. So now, here's my x1. If I was doing a half space, and I have the same old UV divergence, but I also have an IR divergence in the m goes to 0 limit. So just to eliminate that, why don't we just decide to cut off the interval, so we make a finite interval, okay? Of length L. And it turns out that you can compute S of A in a CFT for an interval of length L exactly, using some CFT techniques. And I'm going to give you a fake derivation, basically following this, which gives you the right answer. Okay? And I'll sketch out the real derivation, but it would take me too much into CFTs, which you guys might not be, you know, some of you are probably very familiar with, others maybe not. So, so what I want to know is the entropy density. So it turns out that in a CFT, the entropy density at a temperature T, and here I'm going to be precise with the coefficients, 2 pi C over 6 times the temperature. This C here is the central charge of the CFT, which is a number that characterizes the number of degrees of freedom of the CFT. So simplest example, a single free scalar field has C equals 1. A single free fermion has C equals a half. Those are your simplest examples, okay? And you can calculate the entropy density if you have CFT at finite temperature exactly. So this is an exact formula. Assuming you have constant temperature. But now I'm going to do something illegal, and I'm going to just integrate this when I have a situation with varying temperature. Okay? So you get that at least the UV divergent part of S of A is integral down to epsilon dx1 s of 1 over 2 pi x1, which is, when you plug it in, minus c over 6 log epsilon. So at each of these things, we have a divergent piece which looks like this. We have two of them. So this is for each endpoint, which implies that S of A, in terms of the epsilon dependence, is c over 3 log 1 over epsilon. Well, this doesn't quite make sense because I'm taking the log of something dimensionful. We better make the argument of the log dimensionless. What else have we got? The only other thing we've got is L. So we better put an L here. And so we've bootstrapped our way to know the L dependence. And there can't be anything else because there's no other epsilon dependence. So if we had another L dependence, we would have to have an epsilon dependence, but we already know the epsilon dependence. So now we know the L dependence, which is that it's logarithmic. Okay? And furthermore, we know the coefficient, c over 3. And this, if you don't trust this, which you shouldn't, it can be checked by an honest CFT calculation, which goes like this. You again go to Euclidean space, you compute this, trace rho A to the n, which you do, so rho A looks like this for my interval. It's a Euclidean path integral where I fix the fields phi naught A prime, phi naught A on the top and the bottom of a slit of length L. That's rho sub A. I take rho sub A to the n, so I take n copies of this, n sheets, and I glue them together cyclically. So I have n sheets, and I evaluate the partition function on this n-sheeted Riemann surface. But this n-sheeted Riemann surface is very simple because it's actually just a sphere secretly. And so you can actually just compute it exactly in an arbitrary CFT. It depends only on the central charge of the CFT. It depends on no other properties of the CFT. Oh, you glue them cyclically. So the top of the slit of this sheet gets glued to the bottom of the slit of the next sheet, and so on. And then you take the limit n goes to 1, and in the limit n goes to 1, you get trace rho log rho. And you recover this. This is kind of the same story as we had with the topological field theory. If you have a spin chain, which you have reason to believe at long distances is described by some conformal field theory, in other words, you've tuned the parameters to criticality, it's very hard to know, actually, what conformal field theory it is, in general. This gives you the easiest way to find out at least the central charge. It's very similar to the topological entanglement entropy. Okay? And you can, if you find C equals 0, then you didn't have a critical spin chain. If you find C not equal to 0, you have a critical spin chain. Now you could ask, how do you extract the L dependence given that it's polluted by this epsilon dependence? Well, you do something very similar to what we did before with the topological thing. You define C of L to be 3 L ds of A dl. So if you can do this as a function of L, fit to some curve, take these derivatives, it'll tell you the central charge, okay? And the epsilon dependence drops out. And I want to say that you can also compute this exactly in an arbitrary CFT at finite temperature. And this is what you get as a function of L. Well, this is maybe not so illuminating, but I'll sketch it out for you. This is what it looks like as a function of L. At first, for small intervals, it looks the same until the interval is larger than 1 over t, and then it acquires. So whereas this would have been logarithmic, at 1 over t, it acquires a linear piece. Looks like this. So this linear piece is, well, where'd it go? 2 pi c over 6 TL. So if you expand this at small TL, you recover the log. If you expand it at large TL, you get this. Not too hard to see that. Okay? Now you could ask, okay, what happens in a massive theory, or what happens if you have, let's say, an RG flow from one CFT to another? And here, I mean, it's hard to do any calculations explicitly, but there are some cases where people have worked pretty hard and done sort of semi-numerical calculations. And what you get, well, so this is what you expect for a massive theory. When L is much smaller than the correlation length, it should look like a CFT. So you should get this logarithmic thing. So here's my correlation length, and you should get the logarithmic thing. And then when L is much larger than the correlation length, it should just saturate. It should just flatten out. Okay? And actually, this, there's only a few cases where people have actually, there's no cases where people have done exact calculations of the entropy in a non-CFT. But there are a few cases where people have done sort of semi-analytics, so that get it down to something where you can kind of plot it on Mathematica. I don't mean you're simulating an entire spin chain. I mean you have some formula which is not quite closed form, but close enough that you can make a plot. And it looks like that. Okay. And I want to point out that these are all concave. This is concave. This is concave, and this is concave. Is that a coincidence? It is not. You'll be shocked to hear. And there's a very simple argument for why, which is the following. So here's my, let me divide up my space into three intervals, A, B, and C. And let me consider the following combination. The difference is ABC minus BC. So that's essentially the derivative with respect to this left endpoint minus AB minus B. That's the derivative with respect to the right endpoint. And this is also the derivative, This is also the derivative with respect to the left endpoint. But without the right endpoint, without this right interval. So the difference between these two is the second derivative with respect to the length. So this is, roughly speaking, like d2 s of a dl squared, a discretized version of that. But the point is that this thing, by strong subadditivity, is negative. Now, so far, this is just, trying to understand why we always got a concave function. But you can actually do much more than that with strong subadditivity. And in particular, this is the last thing I'll do. You can use relativity. This argument applies in a non-relativistic field theory. The entanglement entry will always be concave in any field theory. But if we use relativity, then you can be quite clever. Say it again?
Where, like the general argument you have for concavity, is it restricted to these equal to?
It's, well, in higher D, of course, S is not a function of one variable. It depends on the whole shape. But there's a generalization where essentially the mixed second derivative with respect to deformations of the shape is negative by strong subadditivity. But you don't have such a simple form where you just say it's a function of one variable and that's a concave function. You're in some function space. So if we have relativity, then we can do the following trick. This is Cassini and Huerta in 04. So now in time and space, you can consider the following type of configuration. So here's A, here's B, and here's C, and these are null. And then you know that if you ask about S of AB, that actually is a function of this AB here is the same as if I just cut across here. So actually, it's a function of the proper distance between this point and this point. And C is a function of the proper distance between this point and this point. And then you have B, ABC, which is a function of the proper distance between this point and this point. And it's a simple thing to prove that these lengths obey this. And that implies, so then strong subadditivity implies, by a similar argument, that S is concave as a function of log L. I just take the log of both sides here, and then I apply the same argument, and that implies that this function C of L has a negative first derivative, which means that under RG flow, so the C at the UV fixed point is larger than C at the IR fixed point, which is something we already knew. This is called the Zamolodchikov C theorem, but Zamolodchikov proved it very differently, thinking about correlators of the stress tensor. So this is a proof using entanglement entropy of that fundamental relation in one dimension. And tomorrow, I'm going to show that, well, I'm not going to show, but I'm going to tell you that actually this can be generalized to 2 dimensions, where it tells us something we didn't already know about 2-dimensional field theories. And I'll stop.